Okay. Last time we were discussing about activity and how activity is a spontaneous and random process. These two terms should have exact meaning. The random in this case does not mean that whether the radioactivity will happen or will not happen. No. For example, if we have a sample that contains n number of radioactive nuclei, what is random about radioactivity is that we cannot predict which one of those n radioactive nuclei will perform that radioactivity next. This is what is meant by random nature of uh, radioactivity. The next term is spontaneous. Spontaneous means that radioactivity will happen no matter what. It will happen the way it is supposed to happen no matter what. It is not affected by any physical change. We cannot change any circumstances around a radioactive sample to speed up or slow down the process. We believe this thing to the extent that that helps us to find age of different old civilizations. Uh, I think you're familiar with the term carbon dating. What is carbon dating is that we can predict to a very high accuracy age of any fossil, because we can predict the number of radioactivity that should be there uh, when the sample was fresh, and the radioactivity that we are receiving now, and the spontaneousness is that it would have happened the way it should have happened, regardless what were the condition between those 5,000 years. There were days of very high temperature, there will be days of very cool temperature, there can be very dry seasons or like wet seasons. But we believe that activity is spontaneous. It happened independent of any physical conditions. So that is why we can predict age of different fossils uh, based on carbon activity in that sample. So carbon dating is based on the belief that the radioactivity is spontaneous. Now, when we see a radioactivity graph, this is how we see it. Like, do you see the fluctuations over there? These fluctuations are because of the random nature. Because sometimes activity will speed up, slow down. Uh, the process is random. That's why we can see the fluctuations over there. But you can on the in the same diagram, you can also see a very fixed trend over there. There is a trend of decrease with a rate which is decreasing as well. You can see that the graph is not only it is a negative gradient, but the magnitude of the gradient is decreasing. So activity is slowing down as well. This shows a very fixed, rigid trend. And this is because of the spontaneousness. Now, these are the curves that we see for activity and for the number, because we already know, we already discussed that activity is directly proportional to number. So whatever happens to activity happens to number as well. Activity and number are directly proportional. So the values on y-axis will be different. For number, the values will be different. For activity, the values will be different. But the curve, the shape of the curve is exactly same. Okay. Now, I hope you remember this formula. Now, this is a formula for an exponential decrease, exponentially negative gradient. Uh, we have already done this formula around 5 other times. We did it for ultrasound, we did it for X-rays, we did it with capacitance. In capacitance, we did it for voltage and for current. So this formula keeps appearing again and again. Okay. So what are the numbers over here? What is A? A means activity after time t. What is A naught? Activity when time is zero, t equal to zero. E is a mathematical constant. Lambda is a is decay constant, and t is time. So activity equals to initial activity into e power minus lambda t. In this case, if we need to find A or we need to find A naught, that is very easy. We just put the values in, get the answer out. But if we have to find any one of lambda or t, then the things become a bit complicated. How can we find t? Answer is, to find t, we need to make t come to the ground level. And to do that, we can take log on both sides. So here we go. When we take log, we get something like this. Now, if you also take math, you will find it very easy. But if you don't, then it can be a little bit of problem, and you might have to then remember some of the things. Now, how did we get to this point? Look, if we have n equals to n naught e power minus lambda t, take log on both sides. So it will become ln n equals to ln n naught plus ln e power minus lambda t. If things are multiplying, they get added when we distribute log on it. Now, we also know that ln e equals to 1 and ln x power y equals to y ln x. So the power comes back and multiplies with the log. So let's see. Ln n equals to ln n naught minus lambda t. Ln n equals to minus lambda t plus ln n naught. So if we plot the graph, y equals to mx plus t. If we plot the graph of ln n on y-axis against t on x-axis, the gradient will be the decay constant, negative of the decay constant, and y-intercept will be a log of the starting number. So we can apply this on both. We can apply this for activity, we can apply the same mathematics for number. So see, ln activity equals to ln activity at the beginning minus lambda t. The gradient will be negative lambda. Negative lambda. Okay. Any confusion till now? Okay, if no problem, then we can keep going forward. Half-life. What is half-life? Last time we were discussing that activity is directly proportional to number. So when activity is happening and original nuclei converting to some new nuclei, the number of original radioactive nucleus is gradually decreasing. So activity because of that radioactive sample should also decrease because the number is decreasing, so activity should decrease. So when activity is decreasing, uh, because of the number, there will be a time when activity will become exactly half. With the passage of time, radioactive nuclei are converting into new nuclei. So the number of original radioactive nuclei will be decreasing. And when number decreases, activity also decreases. If activity is decreasing, there will be a time when activity will become exactly half of its starting value. That time when activity becomes half is known as half life. And it is not necessary that it has to start with a certain value. Um, we can have any starting value. Like for example, if the curve is given like this, we can pick any value as the beginning value and then find half of that value, and the time interval between these two will be half life. So this is how we can do it. And there is also a calculation method as well, which is far more easy. So we can find half life from the graph. We can also find half life using formulas. Let's see the formula. Mm, the symbol for half-life is T half, and unit will be seconds or hours or days. Now, here we go. At the start, at T equal to 0, activity is A naught. Half-life is T half. Activity after one half-life should be activity after one half-life is half of its starting activity, A naught over T. So A equals to A naught minus lambda T. We are putting values in. We rearrange, we find log, and here we go. By doing some simple mathematics, and you can repeat it if you want to confirm it by yourself. You can do it right now. When you start with activity equals to A naught E minus lambda T, you end up with T half equals to ln2 over lambda. ln2, which is 0.693 divided by lambda, that is half-life formula for any substance. And remember, every substance has its own decay constant and its own half-life. Okay, this is all that we need to know for radioactivity. We are all set to do some past paper questions. Here we have the first question. No. Barium, this is produced, just 1 second. Barium 74 is produced in no, it is not barium, it is beryllium is produced in the upper atmosphere and then sinks down onto the Earth's surface. Nuclei of beryllium 7 decay with the half-life of 53.3 days to form stable nuclei. The activity of a sample of beryllium 7 on a tree leaf is 39 millibecquerel. Show that the decay constant of beryllium is 1.5 into 10 to the power minus 7 per second. Now, decay constant. How many different formulas do you know for decay constant? Number one is activity equals to lambda n. But the problem is we cannot use this one because we don't have activity. No, we don't have activity. No, we do have activity, but we don't have number of radioactive nuclei, so we cannot find decay constant this way. Now, another formula is A equals to A naught E minus lambda T. Again, in this one, we need two different activities to find lambda and the time interval between them. Nope. Another formula is that half-life equals to 0.693 divided by lambda. In this case, we need a half-life to find out lambda. So which formula you think is the suitable formula for this question? My selection is
Sir,
good, the third. So in that
सर
one,
ये जो
yes,
एक्टिविटी वाला जो फॉर्मूला है उसमें जो हम अगर a ओवर a नॉट लिखेंगे तो वो हमेशा 1/2 के इक्वल नहीं होगा.
in case if you're putting time equals to half-life, yes.
सही, ऐसे ठीक है.
Not for all the times, but if time is exactly one half-life, then yes, A over A naught will be 1/2.
सही सर.
So lambda will be equal to 0.693 divided by half-life. So it will be 0.693 divided by 53.3, which has 365 days. Each day has 24 hours, and each hour has 60 minutes, and each minute has 60 seconds. So see, can somebody do it with a calculator and confirm if the answer is 1.5 into 10 to the power minus 7 into significant figures or not?
Sir, half-life to 53.3 days.
Yes, it is. मेरा ख्याल है मुझे रोजा फील हो रहा. My bad. It is 53.3 into 24 into 16 to 60. So done. Is it 1.5 into 10 to the power minus 7?
Yes sir.
Thank you. So it will be 1.5 into 10 to the power minus 7 per second. Hence shown. Now, determine the mass on beryllium, the mass of beryllium on the leaf. Now, this is how I intend to go forward. Can I do A equals to lambda n? Can I use this one to find n? Then n means number of radioactive nuclei. Now, each radioactive nuclei has a mass 7U. U means atomic mass unit, where U equals to 1.66 into 10 to the power minus 27 kg. So, after we find n, we can, each n has a mass of 7U, and then each U is 1.66 into 10 to the power minus 27. And this is how we can find the total mass of the beryllium on the leaf. Activity is 39 millibecquerel, 39 into 10 to the power minus 3. And the K constant is 1.5 into 10 to the power minus 7. Can you use this information to solve the question? Now, first of all, you need to find number. For number, what you do is you divide activity with the decay constant, and then this is n. This is n. N means number of radioactive nuclei. This is mass of each particle. Now, mass of each nucleon or each particle. So mass of each nucleus is 7, and mass of the each nucleon is 1.6 into 10 to the power minus 27. And when we multiply every number, we get the total mass. And my answer is 3.02 into 10 to the power minus 21 kg. Okay, you can confirm if your answer is correct, or if there's any difference, you can also check. Any confusion? The leaf is covered so that no further beryllium is added to the existing sample from the atmosphere. Calculate a time that must elapse before the activity of the sample is reduced to 2. So here's the data. Initial activity is 339 millibecquerel. Activity is 2 millibecquerel. Time is what we are looking for, and decay constant is 1.5 into 10 to the power minus 7 per second. So what formula we can use, and how can we find this T? So if you are picking this formula, activity is equals to A naught E minus lambda T, then yes, you can, but it will be a very long method, and I will consider it as an incorrect choice. On the other hand, if you remember this, ln A equals to minus lambda T plus ln A naught, then you can save some of your steps. So T will be equal to ln A naught minus ln A divided by lambda. So it is ln 39 into 10 to the power minus 3 minus ln 2 into 10 to the power minus 3 whole divided by 1.5 into 10 to the power minus 7. Can somebody put everything in a calculator? And find this answer? Ln of 0.039 minus ln of 0.02. Sorry?
19.8 times 10 to the power 6.
19.8 into 10 to the power 6. Is this what you said?
Yes, sir.
Is it 19.8 or 1.98?
No, sir, 19.8.
Then it has to become 1.98 for the standard form and 10 to the power 7. Okay. Just one second. Let me just solve this one. I'm getting 1.98 into 10 to the power 6. Anybody else? Can somebody confirm or deny, please?
सर ये जो आपने बोर्ड पे लिखा है वही था.
Okay, then I might be getting it wrong. 19.8 into 10 to the power 6, then it is. But this is how you solve it, okay? You cannot use this form of this formula. But the problem is because you're looking for the time, and time is in the power, in the exponent. So you have to convert it into a linear equation and then solve it for t. So, I'm sharing this PDF with you guys after the class, and you can solve the rest of the question. कल हम लोग करेंगे एस्ट्रोफिजिक्स स्टार्ट करेंगे, ठीक है? एस्ट्रोफिजिक्स करेंगे कल, कोशिश उसको शुरू से स्टार्ट करेंगे और दो से 3 दिन में खत्म करने की कोशिश करेंगे. उसके बाद फिर हमने पेपर 5 स्टार्ट करना है. ओके, एनी क्वेश्चंस?